When we look at the idea of power, whose basic definition is the rate at which work is done, so net work divided by time. Remember, anything divided by time is a rate function. It seems at first pretty straightforward. However, we know there's a very intimate relationship between work and energy, and the question might arise, is power also related to energy? And the answer is absolutely. When I'm talking about power, I might be looking at mechanical work, physically, say, pushing a ball across the floor. But I might also be looking at how the kinetic energy of a system has changed per unit time. A change of energy does require work, and therefore, looking at kinetic energy change, which we know is a measure of the network in a system, per unit time, would also equal power. Well, what about potential energy? Well, if that changes, I move something up and down, I change the gravitational potential energy, or I compress or stretch a spring, elastic potential energy, those changes are all caused by work. And therefore, tracking changes in potential energy per unit time would also be looking at measuring power. So sometimes it can be a little difficult to figure out how do I approach problem solving when I have to deal with power. We have to add in another layer of complexity on when we start to think about how do we calculate some of these variables. So for example, net work is net force times distance. So we know, because we've had to do it many times in many ways, finding displacement through some kinematics, or net force, whether it's using some calculations involving friction and an applied force, whether it's finding acceleration using kinematics and a mass of an object. Working out this numerator might take some effort. And of course, working out these guys is going to take a little effort as well. So, is this it? Is this the extent of the formulas we have to look at? Well, no, there's still another one. When I'm dealing with power, and I think about this particular formula here, which is looking at net force and time, net force, distance, and time. Another way to think about this formula mentally is to think about it as our force times distance over time. I still get the exact same formula, force and distance in the numerator, time in the denominator, but we know another identity for this particular combination. We call it velocity. So another formula, when I'm looking at the calculation of power is force times velocity. Force times velocity. This is especially good if you know somebody's moving at constant speed. If someone's moving at constant speed and you can solve for the force that's acting in the system, then that's a nice quick way to calculate power. So let's look at some examples where these formulas are used and why maybe I would choose one formula over another. Let's say I have something like, and I don't know, it could be a basket that has a mass of 1,200 kilograms. Okay, so this is a big industrial basket. We're lifting coal from a mine or something along those lines. And that basket needs to move 7 meters, perhaps from the bottom of the mine to the top, and it's being lifted by a winch whose power is 8,000 watts. Now, if I'm moving something, there's going to be friction in the system. So there's some friction here also of 700 newtons. My question is simply, how much time is this going to take? How long is it going to take to actually lift my bucket, or from down here at the bottom of my mine or the bottom of a building, all the way to the top, 7 meters, using this particular winch? So if I was actually in a real life situation, that would be a very important question. I've got to lift things perhaps at a certain rate. I have to evacuate a product at a certain rate, or move people, perhaps it's an emergency situation. We're lifting, injured people from a scenario. I've got to get them up at a certain rate that's not too fast, too slow, etc. So solving for time is actually very common in these problems. Well, I have a body of information. I see it there in front of me. And I have to think of all the possible ways to calculate power. Power, work over time, which is force and distance over time, which could be the change of kinetic energy over time, which could be the change of potential energy over time, which could be force times velocity. What in the world do I choose? Well, start by looking at your information. I've got power. Well, that doesn't help because all my formulas have power. But I am given information about displacement. Now that displacement, with no information about velocity, there's no VO or VI or VF in here anywhere, that starts to take out certain things from our calculation. One, this guy's probably going to vanish. I have no information on velocity, and I don't even really have a way to get it. He's also out of the equation. Same reason. Under this one of my potential energies is elastic, and I'm not dealing here with a spring. I wasn't given a spring constant or anything like that. So that guy, for at least elastic potential energy, is out. But I might think about gravitational potential energy and time. That could be something I would want to keep in mind. And then look at my data again, and I see I've been thrown some information about friction. So seeing as how they're giving me some information about force, it's probably a good idea to look at the formula left that has force in it. That guy's out. But this guy could definitely be a possibility. So my mass of 1,200 kilograms and my distance of 7 meters, my power of 8,000 watts, or if you want to say 8 kilowatts, my force of friction was 700 newtons, and I'm solving for time. Well, looking at these, I should probably gone back, and if I was actually using my brain, I would have remembered that this formula doesn't even have time in it. So when we struck him out based on velocity, he also doesn't have the variable I'm looking for in terms of time. Now maybe I could have gotten to him through the distance time piece, because I do have distance divided by time, but there seems to be an easier way to go. So he's now struck down for 2 reasons. And chances are this one might be the direction I'm going. Now what I'm ultimately looking for is the time, and thinking about this idea of net force, I have to ask myself the question, which forces are involved in my system? Well, I actually have 2. One is that force of friction, downward. But I can't forget about the weight of the object. He is pulling me down as well. Now I'm given no information about an upward force, a pulling force. I'm not told that we are moving at an accelerated rate. Those are all sort of clues that my problem is saying these are the 2 guys who are involved, and that what I'm likely doing is taking the value for each of these and setting those equal to the upward force being provided by the rope on the bucket. Now if they gave me some additional information about a final and initial velocity at time, if they were leading me towards acceleration, then I would probably be looking for this value here to be a different value than the sum of these 2. But this one really sounds like I'm going to go ahead and use the sum of these 2 forces to balance the force of the upward pull, and that's the force then that's going to go right there. I know it says net force, and you would say, well, the net force in this system is 0. Well, I'm actually looking for, because I'm given power of the winch, that force would be the force provided by the winch. And seeing as how he will balance these guys, he'll be a non-zero value. So alrighty, we've got our formula. We've thought about the problem, we've looked for any places to get extra information, we've made some assumptions, and that's pretty typical for what we do. So my 2 forces acting downward was the weight of the object, so weight is mass times acceleration due to gravity. plus 700 newtons. That force right there times the distance, which is 7 meters. I'll make myself a little room here. Okay, plus 700, bloop and bloop, times 7 meters, divided by our unknown time, would equal that nice 8,000 watts that's staring us in the face. So 1,200 times 9.81 meter per second squared plus 700 times 7, that value divided by 8,000, you're going to wind up getting a time of 10.95 seconds. And there you have it. Could I have attacked this with that potential energy idea? It didn't have force, but sure as heck had distance, and I know it contains mass. Well, you could have. What you might have forgotten about a little bit, though, is this one. Stating this, or thinking about it in terms of net force and forces acting and the force of the winch, this one might make a little bit more mental sense. You might forget about friction if you were just looking at the idea of gravitational potential energy. And thinking about, I'm not just looking at the power in a net situation, I'm looking at it in terms of the perspective of the winch. So you would be a little off if you use that formula and didn't think about friction. Well, about some other examples. Well, we could have an example where, let's say, I have something, it could be a ball, it could be a cart, say it's a little cart, and he's moving along, starting at 1.5 meter per second. So he's just tootling along. He's going to accelerate until he's reaching 2.8 meter per second. So I have a little cart moving along, has some acceleration, his speed changes. Given that change of speed occurs, not V equals, T equals, in 4 seconds, and the mass of my cart is 60 kilograms, again, what power is being delivered in terms of my little cart? Since I'm not given any information here about friction or anything along those lines, I'm not even going to put it into my head. But again, I have that whole list of formulas. And I have to try and think, based on my different formulas, which would be the best fit. So, P. Well, I am given some velocity information, but I'm given two different ones. I'm given a mass, and I'm given a time. So even though I have a velocity, they give me 2, and they give me a time value as well. I can hold him on the back burner, but for right now, I'm just going to say, for my purposes, I'm not going to think about that one right away. The one that jumps most quickly to my mind is this one. Kinetic energy, we know, by himself, is 1/2 mv squared. Well, I've got mass and velocity, both initial and final. I got my mass, and I got my time. That seems like a pretty quick way to go. So, I start working. After I erase all this mess. Erase, 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 erase. Have fun erasing. Alrighty. So I'm going to say now power is change of kinetic energy divided by time. My kinetic energy would be 1/2 final velocity squared times mass minus 1/2 initial velocity squared times mass. I put my numbers in, 1/2, I've got 2.8, oh excuse me, I didn't write my mass down properly, that's a velocity. 60 kilograms, 2.8 squared, I know I'm leaving the units off, but it's to save space. 1/2, 60, and the last velocity, 1.5. all of that divided by 4 seconds. So I have all the information for the final kinetic energy based on the final speed and mass, all the information for the initial kinetic energy based on initial speed and mass, and I have time. When I solve for it, power turns out to be 42 watts. So you might ask yourself, would there be a possibility that that other formula that involved velocity could be used? Did you throw it out and it shouldn't have been thrown out? Well, I threw them out because one looked a little quicker to me, one looked a little more like it matched the information. But we could always explore that formula, which was power is force times velocity. Now, in order to work with the idea of force, I would need to know something about the mass of the object, which I have, yay for me, right there. But I would need acceleration. Ooh, look at that, I can get acceleration. Acceleration, final velocity minus initial divided by time, and I have all of this information. That times the mass would give me my force. Well, what about the velocity? Well, this is accelerated motion. He's not moving with constant speed. Therefore, when I look at the idea of that one single velocity value, there isn't one. But could I perhaps use average velocity? I have two values, so 1.5 meter per second plus 2.8 meter per second divided by 2, or multiplied by 1/2. And what you find is if you take this value here, the average velocity, and you multiply it by force, yes, you do get the same answer. So you could have used either formula. The kinetic energy change seemed to most closely match my information set. However, I could have used this one if I, in my mind, thought about how I would put something for that velocity. I can't use final, I can't use initial. I would have to use an average of the two. So, two ways we could have worked that problem with two possible different formulas. Well, how about a third one? I am going to lift an object who has a mass of 900 kilograms from one position, x1 or y1, of 15 meters above the ground, to a second that's 32 meters above the ground. This is going to take me 6 seconds. How much power did I deliver in lifting this object? Well, I've got a change of height, I've got a mass, I've got a time. First thing my brain goes to is power is change of gravitational potential energy divided by time. For my change of gravitational potential energy, I would have my mass, 15 meters, oh no, 900 kilograms times gravity times the second height of 32 meters minus 900 kilograms times g times the final height, minus the initial height of 15, divided by my 6 seconds, and I wind up getting 2.5 times 10 to the 4th watts, or 25 kilowatts. So if I'm lifting something up and down, instead of going through the force and distance type of a situation, if my brain is not thinking that way, you might be thinking about, well, he's changing height, going from one position to another. That's a change in gravitational potential energy, and this would be a way to look at it. Of course, some of you might be catching on to the fact that mass times acceleration due to gravity is nothing but weight, or a force, times the distance. In other words, it's still looking at the idea of work. But we know the work I do on something is what changes its energy. So thinking about it in terms of, again, force and distance or a potential energy change, both would get you to the right answer. What though if it's a spring? I have a spring with a spring constant of 5,000 Newton over meter. The spring's in a machine, and as the machine works, it stretches and compresses my spring 7 centimeters. It does this every 2 seconds. What power is being delivered by my machine on the spring? Well, right away, seeing that nice fat K, I'm thinking this would be something that would link our potential energy, elastic, to our power. Now we know that this particular stretch is in relation to a 0 length. So our initial position is 0. Our final position will be 7 centimeters. Power, 1/2 the spring constant, times the final position of 7 centimeters. We cannot forget to turn that to meters, squared, divided by my 2 seconds, and you get 6.1 watts as your power delivery. So obviously this one's pretty quick. As soon as you see that spring constant, the brain goes immediately to elastic potential energy. So that was a pretty quick one to use. So when I'm looking at the idea of choosing formulas, I always go to the trouble writing down my information like this. I know I do it on the board in class, but I do it when I'm solving problems at my desk as well. That way, with this list of variables, I can look at formulas and see how many of them best match different formulas. If none of them seem to work right away, question 2. With the information I have, can I solve for more information? Can I add an initial velocity or a force or something like that to my list in order to now fit one of my existing formulas? And sometimes I can, and sometimes I can't, and I may still have to try and think of something else. Perhaps a formula I have totally forgotten about, and when I look at my formula sheet, there he is. Or perhaps it's a stranger relationship where I'm actually having to almost come up with my own formula in order to get to the answer. But in general, list out your information. And don't just write down 5,000 Newton meter and 7 centimeter in 2 seconds. Go ahead and write down K equals, delta X equals, T equals, A equals, M equals. Look then at who those guys would be in a formula and use that to help you try and pick out the right answer. Alrighty, so exam tomorrow for CP Physics, and we'll see how that goes. I'll be here tomorrow before school if you need anything.